This video demonstrates calorimetry using a coffee cup. Coffee cup calorimetry is very good for enthalpy change reactions in which a solid reacts with a liquid or two liquids react together to give a temperature change. In this example, I'm using magnesium ribbon with dilute sulfuric acid. The first thing you'll note in this stage of the reaction is the magnesium ribbon is in quite big pieces, so hence I can measure its mass with a top pan balance by measuring it on a filter paper. Now normally if the solid was in a powdered form, a filter paper would not be a good suggestion because the powder would adhere to the filter paper. In which case it would make your measuring of the mass of the solid that you're going to use a little inaccurate, in which case you would have to measure the mass at the start, and then you would, having used the solid, you would then have to re-measure the mass of the filter paper to measure and determine exactly how much solid you had used. So first stage then, as said on the screen, is to record the mass of the magnesium which is being used in this experiment. First calculation we have to do from this experiment is to work out how much energy is released and given out and put into the acid. And there's a fairly standard equation which keeps cropping up in this particular topic of enthalpy changes, and that is energy, given the symbol Q, equals mc delta T. Now this is worth a little bit of explanation. M stands for mass, and in this case it's the mass of liquid, the dilute sulfuric acid, in grams. But M represents the mass of anything in the experiment that you are measuring the temperature change of. As I said, in this experiment it's the change in mass, it's the change in temperature of the sulfuric acid. C refers to specific heat capacity of the substance which is effectively changing temperature. Again, in this case, it is the sulfuric acid. And delta T is the temperature change. So, substituting in some of the numbers, we arrive at the final solution to this experiment. Q equals 25, which is the volume of the dilute sulfuric acid I used in this experiment, 25 centimeters cubed. Again, I'm making an assumption here, which is often done, that the density of the liquid is the same as the density of water, which is 1 gram per centimetre cubed. Hence, 25 centimetre cubes equals 25 grams. Times the specific heat capacity of, again, the assumption is water, which is 4.18 joules per gram per degree C. And this number, the 4.18, would be given to you in any data tables in the exam question. And 33 is the temperature change. So if we put these numbers in this experiment, the energy change which occurs when we put the magnesium into the dilute sulfuric acid, we get 3,448.5 joules. But we need to remember that that 3,448.5 joules is produced by 0.004 moles of magnesium. And the standard practice here, if we look at the equation, is to quote our energy change per the equation. So in this case, we need to write it per moles of magnesium, and the equation refers to 1 mole of magnesium reacting with 1 mole of dilute sulfuric acid to make 1 mole of magnesium sulfate and 1 mole of hydrogen gas. So the energy change is the energy change for this reaction divided by the number of moles of the magnesium which cause the energy change, or cause the enthalpy change. So it's 3,448.5 divided by 0.004, the moles of magnesium, which gives us an energy change per mole of 862.125 joules per mole. And again, the normal standard practice is to turn the joules into kilojoules. So I've divided this number by 1,000 to give a final answer of 862.125 kilojoules per mole. And here is the summary of the reaction. The standard enthalpy change of reaction as measured in this experiment is 862.25 kilojoules per mole. Because the temperature is increasing and going up, the energy change we show is as an exothermic reaction. And the minus sign indicates that the energy is given out. I hope that helps with this type of practical and question. Thanks.